All right, so let's start with number 6 here. We've got basketball player passes a basketball down the court for a fast break. The ball leaves player's hands at this speed and slows down to this speed at its highest point. How high above the release point is it when it's at maximum height? All right. So first, doing our y here, and I'm going to add in, guys, I know, a little quieter, if you don't mind, gentlemen in the front row who are. I'm going to add in a column of PE grav, and of course I'll put that on both sides. When the ball starts, I'm going to say that it has all KE, so I'm going to take that the potential energy, gravitation at whatever height the person releases it is 0. Because they asked me about how high above the release point. So I'm taking that release point as a gravitational potential energy of 0. Just for make my life easier. Then I know that it's going to gain some PE grav, but it's also going to retain some kinetic energy. So I think I'll bring my kinetic energy down like 3 bars, and I want these to balance, so I'm going to make my PE grav 3 bars there. So I have 8 on the left, no external work because there's no air resistance or anything, and then a total of 8 on the right to flow with that idea of conservation of energy. Questions on the why? Make sense? Agree with yours, hopefully? Those of you that did them?
The question so far is like Periscope, is it all dependent on what you saw as like the left starting point and final point?
Right. So you could have had some PE grav in here, and that would have been perfectly okay. You could have even had some negative PE grav. The big point, I think, in the why, or what I would like if I was looking at yours and trying to evaluate it is, did the kinetic energy that left the kinetic energy become PE grav? If that happened, no matter how you laid it out, then I would give you full credit. If you have that concept. All right? So, let me change my view. Alright, so I'm going to start off with my equations. And then beforehand, in my instance, I said I just had kinetic energy, and I'm going to actually label that initial because I have a final kinetic energy, so I want to make sure that I'm distinguishing between the two. Afterwards, I'm going to have KE final plus PE grav final. Substituting in 1/2 m speed initial squared equals 1/2 m speed final squared plus mgh. And then I would substitute in what I knew. I know my V initial. I don't care about my masses because, why don't I care about my masses? Because they cancel out. So, I mean, you could go through and say, okay, I'm going to find a number for KE initial. I'm going to find a number for KE final and plug those in and then solve. That would work also. Me, I'm going to do the algebra from this point and plug in what I know and things like that and work it through. So, whichever way you want to do it. But I'm going to do a little algebra. But .1, 7. Okay. Cool. All right, so on to number 7, where we have this pendulum swinging. Kind of a little bit of the opposite situation of that one we did in the in-class problems. In this one, we're told a lot about when it's at point B, and then it swings up to point A, and we're asked to find the change in the gravitational potential energy and the speed at point A. There's the part B. Oops. So in my Y, I'm again going to add that. Here, I have it. I'm going to add that PE grav column. And put it on both sides here. And then at the very bottom, I'm going to call my potential energy grav 0 at the bottom of the pendulum swing. And I can place it wherever I like there. So I'm going to say it has just kinetic energy at that point. But as it swings up from point B to point A, PE grav is going to increase. But at the same time, that means its kinetic energy, because gravity is a conservative force, has to get less. And there's no external work because there's no friction or air resistance or anything like that, so kind of identical to the last one. So good on the Y? Okay. One thing is that geometry going on again. Where we have L here and L here, and then this side in here would be L cosine theta. We went over that on the in-class problems, right?
Yeah.
So, need those same equations again. And this was point B, and this was point A. So at point B, we had just kinetic energy. I'm going to label that kinetic energy at point B. That equals our kinetic energy at point A plus PE grab. PE grab at A. And now for part A, all they want to know is is this one here, right? So you can just substitute in there MGH, and here you have the 1/2 M VA squared. Here you have the 1/2 MV B squared. So really what you need is this equation for part B. For part A, you just need to do the PE of G at A is MVH. I think. Let's see. Yeah. Questions or clarifications? When you solve it for B, yes. When you're solving it for A, no. Part A, it won't. Part B, it will. Yeah, because we said it was 0 at the base, we just had to find the new potential energy.
Okay.
Otherwise, if we hadn't, we would have had to find the difference in them. One more subtraction. And if you don't remember how that geometry and the little diagram works, look back to your in-class problem. Because that pendulum we did had all that same geometry in there. All right, so looking at number 8 here, we have this plane starting at rest at the runway at sea level. So I'm going to set my gravitational potential at 0 at the sea level at the runway where it starts. And they're telling us right away that there's a change in mechanical energy. So that means there's external work done on it. And it goes up, so it's going to, in my mind, I'm thinking, oh, it's gaining gravitational potential. And then it also gains speed, so it's gaining kinetic. So my graph, again, I added that P credit. So I'm going to put a bar here. And then I'm going to put another, give it some kinetic energy. make that a more interesting color. And then I'm going to give it some potential energy, and I'm purposely not making those the same, just so that somebody won't say, "What? Do they have to be identical?" Because they don't have to. They can be any ratio. I don't know what the ratio is between them, but I know they have to add up to the work. So that's what I would have for my Y. Good? Good. All right. So, shockingly, I know. So I'm saying that the external work from my Y, the external work done on it, equals whatever its kinetic energy and potential energy is at the end. And so that's what I'm solving for. Nicely, they give me M, they give me G, they give me H, they give me V. Done. Nope. Kind of looking at the outcome, what did that work produce? Well, it produced these energies in the plane.